Hello and welcome to my video on propositions and propositional logic. So today we will cover what propositional statements are, compound propositions, and truth tables. So now, what are propositions? So propositions are declarative statements that have a truth value, and that truth value can either be true or false. So if you've done coding in the past, it's basically the same thing as a Boolean, right? So So here are examples of propositions. So the capital of Michigan is Lansing. Well, the capital of Michigan is Lansing is a proposition because it's a statement that says something, and that statement is true. That car is fast. That is also a statement. Depending on what car you are talking about or observing, that could be true or that could be false. Snails are very fast. Now, this is false, but it's a proposition nonetheless. It states something. Uh, and uh, and propositions can also be in the form of a mathematical equation like this: 5 plus 7 is equal to 14. That is also false, but again, it's a statement, which makes it a proposition. And just like how you would assign, and the thing with propositions is that you can assign it a variable. Like in math, you can say like let x be 7, right? So just like that, we can assign propositions variables. So we can say let the capital of Michigan is Lansing be the proposition P, or let that car is fast be the proposition Q, and so on. Now, there are some statements that aren't propositions that can't be counted as propositions. So, for example, are you finished yet? Well, that is a question, and a question, it can't have a true or a false value. Do your homework. This is more of a command than a proposition. X plus 3 is equal to 8. Now, we don't know the value of x yet, so it's more of a question, I'd say. If we append this with let x be 5 or whatever number, then the whole thing would be a proposition. But since we're only concerned about this portion, this statement alone is not a proposition. And last but not least, hello, that is just an exclamation. That is not a proposition. Next, we will talk about compound propositions. So compound propositions are propositions that combine two or more little like propositions using a connective or like a logical operator. So just again, I'll use math as an example. So we'll have like variables x and x, y, and then we'll have a operator like a plus sign. X and Y are variables, and the plus sign is a operator. So this whole thing could be a mathematical expression. Similarly, with propositions, you can combine propositions and logical operators. So we have six of these, and I'll get into more detail in a bit, right? We have negation, which negates a proposition. We have a conjunction, which is which is basically like saying and. We have an inclusive and an exclusive disjunction, which is basically like saying or like either or. Implication, if then, and a biconditional, which is an if and only if condition. And and on the right, you can see how the connectors are used to combine different propositions. So if I have a proposition P and a proposition Q, just like what I did with X and Y, I can use these connectors or logical operators to make a compound proposition. And just like these simple examples, I can use many operators to make a bigger compound proposition. So for example, if I have he and q and I negate that, and the whole thing is an implication to q. So it might seem like a lot, but bear with me. We will start talking about each one of these compound propositions in detail. So a negation proposition is the most simplest one. This one requires only one logical operator. So if let P be a proposition, the door is closed, then not P would be the door is open because a door it can either be closed or open. Um, and Q if Q is my lanyard's green, not Q could be my lanyard is not green. Simple as that. And if R is a proposition, the car is broken, I could say that not R would be, it is not the case that the car is broken. Again, all these three examples are all ways to say the not operator in English basically. Oh, also I forgot to add, but uh yeah, I forgot to add, but the symbol for not is this. So if I want to write not P, I'd write it something like this. And here let's construct a truth table. So if this is P, construct a table. If this side is P and this side is not P, so P can either be true or false. So if P is true, then not P would be false. And if P is false, right, not P would be true. So all the not operator does is that it switches the value of the switches the truth value of the proposition. And we'll look into what more other operators do. This is the most simplest one. It only needs one proposition, but the other ones like and or it needs like a P and a Q. It basically needs two propositions, and that's where like the truth table is gonna get bigger. Okay. Next is the conjunction, which is the and operator. So an and operator is just like an upside down. It looks like an upside down V basically. And if you want to write a proposition, it would be something like this: P and Q. Okay, these are two separate propositions, and the and operator basically it's basically a conjunction of both of those propositions. So if P is a proposition, the bike will work if it has the front tire, if the front tire is working. And like QB, the bike will work if it has a back tire. The compound proposition P and Q would be the bike will work if it has both the front tire and the back tire. Okay, so that was an example. So if we construct a truth table, so over here we have P, Q, and this side is P and Q. Let me just swap off the color really quick. Okay, there are four possible values that could be tested for here. So if P is true and Q is true, if P is true and Q is false, if P is false and Q is true, and if both P and Q are false. So let's think of it logically, right? The bike will definitely work if both the front and back tire are working. So if both of these statements are true, then the bike will surely work. Now if P is true and Q is false, now if the front tire, if the bike has a front tire, but it doesn't have the back tire, then the bike won't work. So that is false. Now, same thing with F and T. I mean, with P being F and Q being, I mean, P being false and Q being true. If the bike doesn't have a front tire, but if Q has the back tire, it still wouldn't work. And obviously, if P doesn't, I mean, if the bike doesn't have a front tire nor a back tire, it will not work. So as you can see, an and operative is only true if both propositions are true. Okay, now for the next one. So there are two, okay, so now we just covered a conjunction, which is an and, basically an and statement. Now we have a disjunction statement. Now there are two types of disjunction statement, an inclusive and an exclusive one. We'll cover an exclusive one, the exclusive one in a bit. But basically, it's basically an or statement, and which is represented by the symbol that looks like a V. And just like the other propositions, if you want to write a compound proposition, you'd write it like this: P or Q. So here's an example. If P is you can come to school if you, okay, in a scenario where the school is so far and it doesn't have a bus for some reason that you can only go to school if you have a car or a bike. So let P be you can come to school if you have a car, and let Q be you can come to school if you have a bike. He or Q could be you could come to school if you have a car or a bike. So let's make a truth table uh to see where this is. Okay, here's P, here's Q, and here's the value of P or Q. Okay, so as said before, uh, scenario where both of them are true, true, false, false, true. Maybe going over here. Okay, so l- let's say you have both a car and a bike. Well, you can definitely come to school. You can choose either one of them. So this would be true. Let's just say you have a car, but you don't have a bike. Well, that's no problem. You can use the car to go to school. So this statement is true. You can come to school if you have a car or a bike. You can still come to school. If you don't have a car, but if you have a bike, still you have a bike, so you can use that to get to school. But let's just say you don't have either one of a car or a bike. So you can't come to school, unfortunately. It's too far to walk, and the school district doesn't have a bus for some reason. So in this scenario, you cannot come to school. So this would be false. So as you can see, uh, the inclusive disjunction is kind of the opposite of a conjunction, the and or the conjunction, in a way that for the conjunction, the only way it can be true is if both propositions are true. But for this disjunction, the only way it could be false if both P and Q are false. So now let's go to the exclusive disjunction. So now exclusive disjunction is kind of an either or statement, and it is represented by this symbol that looks like a plus, which is in a circle. So if I want to write a compound proposition, I'd write it like he exclusive or Q. Okay. So here's an example. If you needed to get a laptop, if you needed to get a laptop and you had two options, right? You can buy a MacBook or you can buy a Dell laptop. So P or Q would be he bought either a MacBook or a Dell laptop. And here's a truth table for it. Here's a truth table for it. So P, Q, P, either P or Q. Okay. So, okay. So so in this scenario, you can't buy both a MacBook and a Dell laptop in this scenario. So if both P and Q are true, then either P or Q is false. Um, he bought if you buy a MacBook and you didn't buy a Dell laptop, that's fine. You have one thing. So this statement is true. And basically the same thing with the F and T. I mean, with the next scenario. If you don't have a MacBook but you have a Dell laptop, then you can still then the requirement is satisfied. And lastly, if both P and Q are false, so if you don't buy a MacBook or a Dell laptop, like as I said before, you need to buy a laptop. So if you don't buy any of these, this is false. Now let's go to the next example, which is a little trickier. Okay, so now the next operator we're going to talk about is the implication, which is represented by a right arrow, and it's written like this: P implies Q. And this could be read as if P then Q or P implies Q. So here's an example. Let P be it is a weekday and Q be I have to go to class. And P implies Q is read as if it is a weekday, I have to go to class, or it is a weekday implies that I have to go to class. So the truth values for this one could be a little tricky, so bear with me for a little bit. He Q he implies Q. Okay. So true, 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 false, false, true, false, false. Okay. Okay. So assume that these are under normal circumstances where you don't have any weekend classes. So if both P and Q are true, it is a weekday, I have to go to class. Yep, it's true. Um, okay, so it is a weekday, so I don't have to go to class. Well, that could be true. There are holidays on weekdays like Thanksgiving, Good Friday, so in those scenarios we don't have to go to class just because it's a weekday. So that is also true. Now this one, if P is false and Q is true, it is not a weekday, so I have to go to class. This is actually false. Okay? And the last one, if it is not a weekday, the last one where P and Q are false. If it is a weekday, I don't have to go to class. Well, that is true. So now, as you can see, the implication might be a little tricky thing, a little tricky proposition to understand at first, but all you have to know is if you know that this is true and this is true, then I'm sorry, then you'll know that P is also true. Uh, and now to our next one, the biconditional. So now a biconditional is like an implication, but for it to be true, both P and Q should have the same truth values, and it's represented by a two-sided arrow like this. So if I wanted to write like P if and only if Q, then I'll write it like this. So okay, let me draw a quick truth table. Okay, so P is true, Q is true, Q is false, false, false. Okay. So let P be you can log in and Q be you have the correct password. So P if and only if Q could be you can log in if and only if you have the correct password. So if you have both of these, I mean, if you have the correct password, you can log in. So that is true. Now, you can't log in if you have the correct, if you don't have a correct password. So If P is true and Q is false, then that is false. And if you have the correct password, then it's not the case that you can't log in. So if P is false and Q is true, then that is false. And lastly, if you have the incorrect password, then you obviously can't log in. So if P is false and Q is false, then the whole statement P by conditional Q is definitely true. So you see, so this is kind of the opposite of the exclusive or statement. In the exclusive or statement, it can in that comp I mean sorry, in the proposition, that proposition can only be true if both P and Q have a different truth value. And the key for the biconditional is that the tr the biconditional I'm so sorry. This compound proposition is only true, like P by conditional Q is only true if both P and Q have the same truth values. It doesn't matter what truth values they are. It could be both of them could be false, but as long as they have the same truth value, then then the whole statement is true. And I'm sorry if my explanation was a little too complicated or I stammered a little bit, but nonetheless, thank you so much for watching. I hope this video helped you a little bit with uh, compound propositions and truth tables and propositional statements.